Okay, so let's start by recalling what we proved last time. So last time we discussed Zariski Nagata purity. So this is the following assertion. So we have X, which is regular, connected, and we have open subset X such that codimension of the complement is greater than 1. This is a local assertion, so you don't need to assume anything in X. So local rings are always have finite Krull dimensions. So X. Then the assertion is that the embedding of U into X induces isomorphism on fundamental groups. Okay. So removing a bunch of points from a surface does not change the fundamental group, for example, provided that the surface is regular, smooth. Okay, so what we want to do today is, so as a step toward the proof of the main specializations theorem, we want to extend, so in other words, any finite étale cover over U extends to a finite étale cover over X. And so if this condition holds. Now, so today we want to find some abstractions to extending covers over points of codimension 1. So we'll consider first a local situation where we have a cover over a punctured one-dimensional disk and want to extend it to a cover over a disk, possibly over a non-algebraically closed residue field. So this is called Ramification Theory. So Ramification Theory.
Could you remind about the relation of regularity and smoothness over a field? Which one is stronger?
So smoothness over a field implies regularity. And so if your field is perfect, then the two conditions are equivalent. And if not, they are not. But if you have a schema maybe of finite type over any field, then it's smooth if and only if it's regular after base change to an algebraic closure. Okay? So otherwise, you can just take finite non-separable extension of your finite field of your field, and this gives you an example of a scheme which is regular because it's just one point but not smooth. Okay. Да, но иногда они тут совпадают, если. Very good point. So, okay, so setup here is the following. Again, so the picture to have in mind is that we are now, so we will have, I think we will have some scheme X, and U is going to be the complement in X to some to a divisor in X. And so we are going to have a cover over U, and we want to extend it, try to extend it to a cover over X. And the idea is to localize, so this will be our picture. So we'll have some X, some divisor, D, and so the complement is going to be U. And so we will, so if X is regular, then it's to extend the cover over U, it suffices to extend it to a generic point of D. So we will pick a generic point and look at the local ring of X at the generic point of D. So this is a discrete valuation domain, and we will try to kind of study the relation between the fundamental group of the discrete valuation domain and the fundamental group of its fraction field. So setup here is the following. So A is DVR. So K will be its fraction field. And so we also fix some finite separable extension, finite separable extension. Then B will be its integral closure. Well, of A in L. And what else? So we have discrete valuation domain A. We have maximal ideal, the unique maximal ideal, and it's generated. We fix, let pi be a uniformizer. Okay, and K will stand for the residue field. Okay, so so let's well, in our application, this capital K will be the field of rational functions on X. L will be the field of rational functions on a finite étale cover over U. And again, A will be the localization of the local ring of X at the generic point of D. Good. But yeah. So let's start with the following proposition. So first of all, B is a unique, a principal ideal domain. And well, with finitely many prime maximal ideals, and also prime ideals, because it's principal ideal, maximal ideals, M1, Mn. And okay, so yeah, that's the statement. So let's prove it. Well, so A is a discrete valuation domain. So in particular, it's Noetherian. It has Krull dimension 1. That means that B is well, by definition, it's normal. Noetherian of Krull dimension of B is 1, which implies that B is a Dedekind domain. Okay. So what does it mean to say that a Noetherian ring is a Noetherian domain is a Dedekind domain? It means that it's dimension 1. Well, it means that all local rings of B are discrete valuation domains. So that means that B Mi, well, it has dimension 1, right? There are only 0 ideals. All prime ideals are, every prime ideal is either 0, it's a maximal ideal. And saying that it's a Dedekind domain means that this is all local rings are discrete valuation domains, DVR. So why is that? Because this has Krull dimension 1, and it's integrally closed, and every integrally closed domain of Krull dimension 1 is regular, right? So Mi modulo its square is one-dimensional. Therefore, Mi is generated, the maximal ideal here is generated by one element. So I'm using here, well, non-trivial fact about a characterization of DVR as local rings of Krull dimension 1 integrally closed. So, okay, B is free. Well, we also know that because A is Noetherian, B is integral closure and finite extension, that B is a free. Well, so B is finite A module, and because it's also flat, right? It has no torsion, right? Because it definitely has no pi torsion. So B is a free A module of finite rank, of rank equal to degree of the extension. Is it clear? So now if I take B modulo maximal, ну смотри, значит, это конечно порожденный модуль над кольцом дискретного нормирования. Значит, такой модуль является, ну, например, по классификации модулей над кольцами главных идеалов, такой модуль является свободным тогда и только тогда, когда в нем нет кручения. То есть, когда в B нету элементов, которые убиваются умножением на вот это вот самое π. Но B, конечно, в B нет кручения, потому что B — это под кольцо в поле L. Вот. Хорошо, значит, таким образом, из-за классификации модулей над кольцом главных идеалов, конечно порожденных, отсюда следует, что B свободен. Значит, moreover, if I take B modulo maximal ideal, M here stands for this maximal ideal. because if you take B and tensor it with K over A, then you get L. Because да. Ага. Да. Почему? Почему любой элемент? Хорошо. Okay. So therefore, this quotient M here is this M is the maximal ideal in A, is finite dimensional is an algebra. Finite dimensional algebra over K is K algebra of dimension of this dimension. Well, please interrupt me if this material is kind of is elementary, and it's very important that we kind of all understand it well, because it will be used all the time later. Of this dimension, right? Because it's free. So, okay, this is the same as the quotient B tensor A over A mod M. Now, it follows that this every finite dimensional algebra has finitely many maximal ideals, has finitely many maximal ideals, and this implies that B itself has finitely many maximal ideals. Right? I'm using that every finite dimensional algebra has finitely many maximal ideals. And the second implication follows from the fact that if you take any maximal ideal in B, then its intersection with A is the unique maximal ideal. So every maximal ideal in B contains this little m. So there is one-to-one correspondence between maximal ideals here and maximal ideals here. Good. So and that's so. What else? I still have to show that B is a principal ideal domain, right? I have to show that all these maximal ideals are principal. That's enough. It's enough to show, I know by general property of a Dedekind domain, any ideal is product of prime ideals. So you just take the divisor corresponding to an ideal and write it as a sum of divisors, irreducible divisors corresponding to this point. Okay, so why am I a principal? So you have let's prove that M1 is principal. So we will consider the map from B to B modulo M1 squared times B modulo M2 squared times Bn modulo Mn squared. So Let's consider this map. This is the projection map. So I claim that this map is surjective. And this follows from the Chinese remainder theorem. These ideals are relatively prime. If you take sum of this, for example, and this, you get everything, right? Because it's not contained in any maximal ideal. So this map is surjective. And so now take pi I in mi such that its image in B modulo mg is not zero. Not zero for every j not equal to I. Right? So you take m modulo mi squared. That's what I want. Then mi is generated by this pi I. Indeed, every why is that? So this is an ideal. Therefore, because we are in the Dedekind domain, this ideal is equal to the product of powers of the maximal ideal, because pi I is not in mj. For any j is not equal to I, only power of mi appears in this factorization, and because pi I is not in mi squared, we have this equality. This completes the proof. Good. So some notations. So let's set. So we have for every mi, we have the residue field. This is P mod mi. And we have finite extensions, k of mi k. This is a finite extension, and I will denote its degree by fi. And I also introduce ramification indices. So let's we have uniformizer pi in M, and so I can write this uniformizer as product of pi 1 E1 times pi n En times a unit. So U is an element of B star. If you want to do it more invariantly, you would just write pi, look at this ideal, and write it as a product of prime ideals. So this shows that the ramification indices do not depend. F — это некоторые целые числа. Вот они определяются так. Мы взяли униформизующую V, рассмотрели ее как элемент B и записали как произведение степеней вот этих вот пи-итых. Любой элемент из B может быть записан как вот какое-то такое произведение, умножить на единицу. Very good. These are called ramification indices. And we have lemma. If you take the degree of the extension is equal to the sum of EI, FI. I goes from 1 to n. Why that? Well, the proof is one line. So you look at the dimension of B modulo maximal ideal. M is maximal ideal in A. So we already know that this dimension is equal to the degree. On the other hand, this is the same as, well, you write M by this formula and use it so this is equal to the sum of dimensions of B modulo Mi to EI. I use again the Chinese remainder theorem. And using the fact that every Mi is a principal ideal, this quotient is simply, its dimension is equal to sum EI times dimension of B modulo Mi. Dimension over K. And by definition of the degree, this is Fi. This completes the proof. Okay? So this picture simplifies if either A is complete or L is a Galois extension. So here is the picture. So you have spectrum of A. Think of this as a small piece of a curve, and so B. Spectrum of B is a ramified cover. I don't know how to draw, well, something like this. So in this picture, you have 2 points lying over this one, so 2 maximal ideals. So ramification index here is 2, here is 1. But the actual picture is a bit more complicated because you also have, because the residue field is not assumed to be algebraically closed. So you have this Fi appearing here. So good. So remark, if A is complete, for example, the ring of p-adic integers or the ring of formal power series over a field, complete with respect to a matic topology, then M then this number n is equal to 1. So you have only one maximal ideal line over M. So B is itself a discrete valuation domain. Proof? So let's think of B as an A module. Because it's free, because it's finitely generated, it's also complete with respect to M-adic topology. So I can think of B as limit of B modulo M to the LB, right? So now so this maximal ideal in A, well, this M times B, is equal to this product. So when computing the quotient, I can use Chinese remainder theorem, right? For example, I can write B modulo M, B, as the direct product of B modulo these powers of the maximal ideal. I already used this once. So therefore, what we have here, because it's a finite product, it commutes with limits. Oh, sorry, it's a product anyway. So I is 1n of limits of B modulo maximal ideals, right? Yeah, so this is just the Chinese remainder theorem applying to every quotient. And now B is a domain, and this is not a domain if n is greater than 1. It's product. So it implies that n is 1. Good. So this is one possible simplification. And another, which will be more important for us, well, is the following. So let's assume that L is a GLA extension. Ну, смотри, тут написано произведение, прямое произведение колец. Прямое произведение никогда не является областью, потому что ты можешь взять... Вот. Оно является областью только если n равно единице. So assume that L is a GLA extension. Then the GLA group G of L over K acts transitively on the set of maximal ideals. All right? So a picture like this is not possible. In particular, all these degrees, F1, F2, Fn, they are all equal. And also the same is true for ramification indices. And therefore, this formula that we have here reads as follows. So it's the degree is equal to n times EF. Okay, so first of all, so I'm going to show that Galois group acts transitively on the set of maximal ideals. So if we know the assertion, then so for every two maximal ideals there exists an element of the Galois group, say that takes M1 to M2, and this element identifies the residue fields, right? It takes the residue field K of M1 to the residue field of M2, and therefore they have the same invariance. Also here, so this factorization is unique. So if you apply an element of the Galois group, it interchanges this maximal ideals here, and because of the uniqueness, you see that E1 must be, all these indices must be equal. Okay, so proof. So, okay. Let's take. We'll use a very similar argument with Chinese remainder theorem. So let's take. Let's prove, for example, that there exists that the orbit of M1 is everything, right? So let's take a product of over all sigma in the Galois group G of sigma of pi 1. So what do we know about this element? Well, first of all, it's an element of A, right? Because A is because this is an element of K, right? We take it's Galois invariant, and A is and it's also an element of B, and the intersection of K and B is A, because A is integrally closed. So, and also, because it's divisible by pi 1, it cannot be invertible, so it must be an element of M. Right? So that means that this element, this product, is divisible by pi. So that means that this implies that this product of pi 1 is divisible by pi I. Which only possible when one of the factors is pi I itself, right? Sigma of pi 1 is of the form pi is just pi j. It takes maximal ideal to maximal ideal, so it takes a generator to a generator. Right? So, which completes the proof. So we proved that there exists sigma such that sigma of pi 1 is divisible by pi I. So that means that sigma of pi 1 is pi I times a unit. So that means that the orbit of M1 is everything. Good. Now, so what do we have to do next? Yeah, so next I'll introduce some notation. So we have the Galois group, G, and let's look at the subgroup formed by O sigma in J, such that sigma of mi is the same maximal ideal, right? The stabilizer. So the Galois group acts here, and I take the stabilizer. And this is called the decomposition group. Let's see what notation. Okay, GMI. This is called the decomposition group. All right. So here is a proposition. Группа разложения. So proposition. So let's consider this decomposition group. It acts on B and it preserves mi. It takes mi to itself. And in particular, it acts on the quotient, on the residue field. So that means that I have a homomorphism from this group to the group of automorphisms of the residue field over K. And the claim is that this is a surjection. So I'm not writing here the Galois group, because in general, this, though the extension L over K is separable, this extension need not be separable. So it's not a Galois extension. Nevertheless, it's normal. So this is A, and B is, this is normal. So it's a splitting field of a polynomial is normal, right? Proof? Okay, so let's take K. Let's take K of mi. So as I said, it need not be separable, but I have maximal separable subextension. The set of all separable elements. And by the primitive element theorem, I can write this as this extension is generated by a single element. And I will write this single element as B bar. Right? So now I have B. Let's take a so this B bar is an element of the quotient of B modulo mi. So B bar sits here. So I have this projection, and I want to pick a per-image, pick B, such that such that B is in Mj for all j not equal to I. And again, I can do this using the Chinese remainder theorem. So consider now the product, the following polynomial. So product over all elements in the Golgi group of x minus sigma of b. So first of all, I know that this is a monic polynomial with coefficients in a, because b is in b. Monic. Okay. So now I claim that it implies that so what do I want to prove? I want to prove the subjectivity of this map. In other words, I want to show that all conjugates to B bar, all conjugates, which are here, are of the form sigma of B bar for some sigma in the decomposition group. Right? So this implies that all conjugates so two elements in the field extension are called conjugate, are said to be conjugated if their minimal polynomial is the same. So all conjugates of B bar are of the form sigma of B bar, of B bar, right? For sigma in the Golgi group, right? So I first apply sigma to B, this I can do, and then I reduce it modulo this maximal ideal Mi. I cannot do vice versa because sigma does not operate, G does not operate here. Only the decomposition group does. So I want to show that I can take sigma to be in the decomposition group. Observe that sigma of B is 0 modulo Mi for sigma which is not in the decomposition group. Why that? Yes, because B belongs to, so if this is not, if this does not hold, then sigma takes Mi to some Mj. And B is equal to 0 modulo Mj And therefore, sigma inverse is equal to 0 modulo mi. Right? So therefore, this implies that B bar all conjugates of B bar have the form sigma of B bar for sigma now in the decomposition group. So this proves the subjectivity. Катя, вопрос.
Даже не очень понимаю. Вот если сигма не лежит в стабилизаторе вытов, он переводит там и вытов под другое.
МЖТ. Давай докажем, что сигма в минус первый от b будет равняться нулю по модулю m этого.
Сигма минус первым будет равняться.
Ну, потому что это условие, вот это условие, оно инвариантно относительно замены сигма на сигма минус первый. Ну, в смысле, что я мог бы здесь написать сигма минус первый. Это было бы то же самое утверждение. Я же утверждаю, что вот это множество элементов, которые не лежат, оно инвариантно относительно замены сигма на сигма минус первый. Хорошо? Это же подгруппа. Вот с этим ты согласна?
С этим согласна.
Да, хорошо.
Но если сигма минус первый от b равно нулю, почему сигма от b равно нулю?
Ну, потому что давай то же самое рассуждение применим к сигма в минус первый. Если сигма не лежит здесь, то и сигма минус первый не будет. Okay. Good. So we prove the first assertion. The second assertion also follows because what we constructed a polynomial which is a product of linear factors in this field, and B bar is one of its elements, one of its roots. So to show that an extension is normal, it suffices to show that to exhibit a polynomial that has B bar as one of its roots, which splits completely. And we succeeded in doing this. Good. A? Subjectivity.
Yeah.
No, we just proved subjectivity. So you suggested another proof. You are suggesting another proof.
No, I'm trying to. We proved normality.
No, we proved this. What we proved? We proved that, so we have a generate. So first of all, this automorphism group is the same as this automorphism group, right? Secondly, every automorphism here is determined by what it does with the generator. So it suffices to show that for every conjugate of B bar, there exists an element of the decomposition group such that sigma of B bar is your conjugate. And that's what we did. No, the comparison with orders is not that, does not work here because, again, the residue field we don't have, because the residue field is not a separable extension. It's the order of the automorphism group is not what we call Fi in general, right? So good. So now the theorem, the proposition is proven. Now a bit more notation and definition. So we have the decomposition group, the stabilizer of Mi, and we constructed a surjection to the automorphism group of the residue field. And I want to denote by I, Mi, its kernel. And this kernel is called the inertia subgroup. So it's a normal subgroup of the decomposition group. So, well, I will need the following construction. So let's define a homomorphism, called phi, from the inertia group. So I want to describe the inertia group. Well, it could be very complicated, but I want to describe its what's called its staying quotient. So let's define a homomorphism from this group to the group of roots of unity. This is my notation for the group of roots of unity in this field, K of Mi. Right? So this is set of all epsilon, group of all epsilon in K of Mi, such that epsilon to the power E is equal to 1. That's notation. So here is definition. Phi of sigma, phi I of sigma. So I take sigma and I apply it to a uniformizer, to the generator of Mi. So, well, what I get is another generator of Mi. So sigma takes Mi to itself. So this element can be written as pi I times a unit. So that means that it's divisible by pi I. And so this is, what is written here is an element of B star. So, and I will define this as, this homomorphism as this element modulo Mi. So, well, what is written here again is an element of B star. And I project it to the multiplicative group. This is a subgroup of K Mi star. So by definition, this element belongs to this group. Now I will check that this is a homomorphism first, from that this phi is a homomorphism from the inertia group to this group, and then using the order argument, we will check that the image, well, this is a finite group, so image consists of roots of unity. And we will check that they are precisely these roots. So let's check that this is a homomorphism. Well, also I need to first I need to check that this is indeed well defined. So it's what does it mean? It means that I claim that it doesn't depend on the choice of a uniformizer. Right? So if I multiply pi I by unit, this expression does not change. And this follows from the fact that I acts trivially here. This is definition. That's the kernel of this map. So let's check that that phi I is a homomorphism. So we need to check that it takes product to product. Well, so this is sigma 1, sigma 2 of pi I divided by pi I, but I want to write it as sigma 1 of pi I times sigma 1 of pi I over pi I. Right? So, so everything is modulo mi. Now, what happens here is that so this factor here is simply phi I of sigma 1. Now, what is written here is phi I of sigma 2. So I think of this as an element of this residue field, and I apply sigma 1 to this. But my element sigma 1 is the inertia group, so it acts trivially here. So that means that, in fact, they have equality. K-цикл. Да, если бы... Good. So we constructed a homomorphism phi I from this inertia group to this group. And now I want to show that the image lives here. So let's see what we know about the order of this group. So first of all, we have this formula. Ну да. So what do we know about the order of the inertia group? So, so first of all, what is the order of the decomposition group? Well, so that's the order, the degree of the Galois extension. Right? So maybe I will write it here. Okay, so let's do it in several steps. So order of the decomposition group is L over K, the degree, divided by N, right? Because it's stabilizer of one maximal ideal under a transitive action. Stabilizer has this, it's one orbit. Now, so order of the inertia group is this number divided by the order of this group. This is a normal extension, so it's the group of its automorphism is the degree of this extension. So let's see. This is R over K over N times the degree of K mi sep over K. So the degree of this extension is f by definition. F times n is equal to E. Remember this formula. F times n is E. So therefore, what I get is E times the degree of this extension, K of mi K mi sep. Good. So, well, there are two possibilities here. So either, well, so if characteristic of K is 0, then this is, of course, 1. Otherwise, it's a power. This is a power of characteristic of K. Right? Degree of any inseparable, purely inseparable extension is a power of the characteristic. So that means that the order of this group is equal to E up to a power of P of characteristic. So, and let's just observe that M EI K MI is the same as M EI. Inertia group. Just because there are no roots of P, roots of unity in a field of characteristic P. So a priori this is larger, but in fact they're equal. So because this is a homomorphism, the image lives here. Because we have equality, we get the result. Good. This completes the proof. And now lemma, or maybe proposition, that's kind of the most important of all I want to say, is so the kernel of this phi is 0 if characteristic of K is 0, and it's a P group if characteristic of K is P. Okay? So the kernel of this homomorphism, well, it's called the wild inertia group. So, in fact, Stack's project gives another characterization of this kernel. So you see, the inertia group acts on B, and it preserves the maximal ideal, so it acts on quotient of B modulo powers of maximal ideal, right? So you have action of decomposition group on B modular powers of this maximal ideal. It operates here. And this action defines a filtration on this group. Namely, you can consider the subgroup of elements here which act trivially on quotients, right? So just take the kernel of this section. So the largest subgroup here will be the inertia group. It consists of all elements that act trivially on B modulo the maximal ideal. Then you can take the second power of the maximal ideal. And so the Stacks project asserts that the kernel of phi is precisely the kernel of this section when L is 2. But I think that the proof has a serious flaw. I don't know how to correct it. And in fact, I don't know whether it's true or not. So I'm preparing to this lecture. So it works. It's OK if the residue extension of the residue field is separable. Otherwise, it's I don't know the argument. So anyway, so I'm not going to use it. Ну, сейчас давай я сначала докажу утверждение, а потом мы обсудим, что происходит. Значит, proof. Okay, so we have the section, and kernel of phi I acts trivially on M I R modulo M I R plus 1. So R is any number. So I have action of a group on this filtered object, on this filtered ring. It's filtered by powers of the maximal ideal. And by the very definition, kernel of phi I acts trivially on the associated graded object. So first of all, the inertia group, it acts trivially here, right? So it's OK when R is equal to 0. Now, by the so let's look again at this this construction here. So what does it mean? Suppose you have an element sigma in the inertia group. Well, one interpretation of phi I of sigma is the following. You just look how this sigma acts on M modulo M squared on the Zariski cotangent space, right? So the Zariski cotangent space is generated by pi I. So you apply sigma to pi I, you get another element of the Zariski cotangent space. And that's precisely your element of the so it's multiplication by an element. This action is given by a multiplication by an invertible element in this residue field. That's what my phi does. So that means that by the very construction, any element of the kernel acts trivially as identity on the residue field and also on Mi modulo Mi squared. But therefore, because this all, this kind of, this Mi is generated by a single element. So say, M squared modulo M cube is generated by, it's one-dimensional space, is generated by pi I squared. It also follows, well, anyway, it's a ring. It's any sigma here is a automorphism of this graded ring. And this graded ring is generated by elements in degree 0 and in degree 1. So therefore, if it acts trivially on elements in degree 0 and in degree 1, it follows that it's trivial everywhere. Okay.
So it acts on a filtered ring and then
Yes.
sort of like it also acts on the associated gradient.
Yes. Yes. Mm-hmm. So and now I claim that this implies a result. So you have a subgroup. So let's just consider a finite subgroup in any finite subgroup in the group of automorphism of an abelian group. B is itself an abelian group, and it has a filtration by powers of the maximal ideal such that all the quotients are, well, they are P groups, abelian P groups, right? This is just, well, these spaces, these are vector spaces over Fp. So what does it, suppose I claim that, so if you consider any finite subgroup in the group of automorphisms of this guy that consists of elements that act trivially here on the associated gradient, then this group must be a P group. Informally, because it's an upper triangle matrix with one on the diagonal. It's every such element has order power of P, right? It's complete. It's a proof. Agree? So, for example, let's see how it works. So let's consider, let's consider any finite subgroup of the group of automorphisms of this guy. So I look at finite subgroup in the group of automorphisms of this guy that act trivially here and also here. This is a subgroup of the group of homomorphism from this vector space, Fp vector space, to this Fp vector space. And the group of Fp linear homomorphism is definitely a P group. Right? So that proves that the image of this kernel in the group of automorphisms here, so image of kernel of phi in automorphisms of B modulo M I squared is a P group. And similarly, using induction, you can replace 2 by L here. Right? Good. So let me, let's see. So so I think I need to stop here. My time is over. Questions? Yeah, so just returning to the remark that I made. So Stack project has the following claim. Kernel of phi is the kernel of homomorphisms from D mi to automorphisms of B modulo mi squared. Right? So the decomposition group acts on B and preserves the maximal ideal, so it acts on these quotients. And this construction defines, so you have a homomorphism of groups, and this construction defines the subgroups here. Well, classically, they're called ramification subgroups. And so the stack project, again, asserts that this kernel of phi is precisely the kernel, but by definition, kernel of phi is so if you take an element here, sigma, and look how it acts on this quotient, right, on this quotient, all you know is that it acts trivially here and trivially here. And therefore, it's a derivation, k-linear derivation of this algebra, of this field with values in this vector space. And of course, even if it's separable, then any such derivation is trivial, is 0, if the extension is. Otherwise, you may have non-trivial derivations. So you may have automorphisms of this algebra, which are identity here and identity here, but not identity on the quotient, modulo m squared. OK, that's all I wanted to say. Questions? So possibly Ron. Да, можно сейчас. Давайте, может быть, мы, во-первых, закончим. Are there more questions? If not, then let's stop here and I'll see you tomorrow. Да, задачи. А можно сейчас. А как насчет завтра вечером, скажем? Можно? Ну, например, 6. Вам удобно? Или можно до лекции. Вот. Хотите?
Да, давайте лучше до лекции.
Давайте 12. Договорились.